All right. So, okay. Okay. So here we are. Sorry. Nine. Okay. So the test, hopefully you guys, it was enough time for you to do everything. I tried to make it as close to the time as possible. Um, every test is unique, as you can see. But if you did spend the time going over the test in my old tests, then you may have noticed that there's a kind of common theme that I tried to keep with, given the fact that we're still on virtual. And so in this case, I kept it to where you had to do a couple of free body diagrams at the beginning. And then I had two harder questions. I threw in a easy one, which I'll explain in a second, just kind of as a baseline assessment for people. And so these are the two images that we did. And instead of drawing them for you, I'm just going to show you what I drew. Now, I don't expect a masterpiece of art when you do these, but they do have to be legible and be have what they need on them. So one of the things I noticed was, um, oops, sorry. One of the things I noticed was that some of the drawings they weren't exactly where they should have been. And what I mean by that is that you should spend on a free body diagram more than 30 seconds drawing it. So, I mean, you'll see when you get back to your test, because I did mark people down if they didn't draw a free body diagram that was legible and neat, because that's such an important part of this class and will be when you guys go on to dynamics and to C204. So let me go ahead and show you. Go back to so here, focus. There we go. So here's 1A. So you have the disc and, or I'm sorry, you have this weight. And so most of you got it. I put down whether they were thrust bearings or slider bearings, and I defined them. So a thrust bearing has a reaction along the lateral or the direction parallel to its rotation, whereas a slider bearing does not. So A was a slider bearing, so it had no Y reaction, uh, and B did, so it did have. And then you had to put P, you had to put the 120 pounds hanging off and also the weight of the drum, because that was given. If no weight's given, then you assume it's massless. Okay, so most of you got this pretty good. And then the other one here, the second part, you're told that both of these had ball and socket joints. And so in that case, the ball and socket was the can support three forces, but can't support moments. So you have that and that. Some of you did, and this one most of you got too. So mainly the markdowns were if you didn't put down enough forces. Over here, you would not break that apart normally. If you did, you'd have to draw these as two separate pieces. You wouldn't just put six unknowns together when they're together, because remember, this is a free body. So this is considered one structure. And so you're only putting in connections to where it connects to the outside world, which is here, here, and the tension CD and 400 newtons hanging off of that. All right. Up here, some of you did put moments, but if you look at the structure, you also have to consider what the loading is. So these bearings are free to rotate around the y-axis. That's why they're bearing. So they're not going to support a moment. The other thing is um, there really aren't any forces on this to justify moments about other axes. So, I mean, I guess you could argue there was one about the X and a supported moment by the weight of this, but that would have been supported by this bearing here. So none of these bearings had moments attached to them. If you did put them, I didn't mark you down, but just keep in mind of what can support moments and what can't. All right. Okay. So any questions on the free body diagrams? All right.
Hey, Professor, how come
Yes.
the A bearing and the B bearing can support reactions in the X and Y directions?
In the X, only in the X. Oh, what do you mean in the X and the Y? I'm sorry.
Because B has a reaction in the Y direction and A has a reaction in the X direction.
Well, of course. Well, both bearings have a reaction in the X direction.
Right.
And so, because remember what I said is that B is a thrust bearing and A is a slider bearing.
Okay.
Right. That was the first paragraph in there. So that's at the top of the test. So that's a key thing, and that actually came back on the next problem because that's why I wrote a slide. I defined them for you. So that was something you want to keep in mind for the final. So I didn't expect you to know that off the top of your head. That's why I wrote that at the very top of the test that a slider bearing does not support a reaction along the y-axis, which would be the axis parallel to rotation.
Okay, thank you.
Sure. Any other questions on these? All right.
Did you give the units for number 1 as inches?
I believe it said inches. I mean, if you didn't put them, usually, well, for one is if it's pounds, it could have been inches or feet.
Okay.
So
If we made an assumption that it was one or the other, is that fine, and wrote that out as the assumption?
yeah, because when I look at the diagram, I don't see units on it. So yeah, I wasn't too concerned whether you put inches or pounds or inches or feet on that. That wasn't critical. So yeah, no, that's fine.
Okay, thank you.
Okay, so let's look at the next one. Okay, so now this one I put in there just basically a gimme problem, and I don't mean that facetiously. Just really what I wanted to do is just throw in a problem that was just a very fundamental. On something like this, you're just asked to find a moment about a line by force P, and so you're given line B. It specifically says a line from B to O, right? So you know that if in order to get from B to O, you have to go negative 2 in the X and positive 3 in the Y. So that's your directions. And then of course that has to be a unit vector. And that unit vector is of course divided by the square root of the two numbers, so root 13. And then you have to go from one point. So you could go from O to C or B to C. And so I just chose to go for the J. And so as a result, though, you then get to P, and then that force there is just broken down. So you have negative 25 cosine 25 in the I and sine 25 in the K, and that's it. And then it's just that dot R cross P. So I was actually quite surprised that how many of you didn't get this correct. And maybe that's not the people on this call that are here presently, but this was the answer, 1559 Newton meters. Because remember that this is not a vector, it's a scalar. So this was really just a plug-in problem. And so if this is still not making sense, then this is probably a critical point in the quarter where you really need to look at the material and try to understand, where what's not making sense, because that if because it's going to get harder from here when we get into trusses. And so you need to have this fundamental understanding. The other fundamental understanding is this R vector. So you always go from the point of the moment to the force. And I saw quite a bit where people were going from the force to the point. So granted, it's just a negative, but then it does screw up your answer. So some of you got, instead of 1500, you ended up adding, I think it ended up being like 700. Yeah, I have it here. Show you. I'm gonna do this. So you can see here's the drawing. There's the equation. There's our unit vector. There's our R vector. There's P. I haven't drawn it out yet, but it actually ends up being negative 679.7 and 317.0. So you end up with down here, negative 703.3 plus 2262. So some of you with the sign error, you added this to that, you get 29 something. So if you did that, that's a couple points off. Mainly when I grade, I look for this here, but I really wanted you to get this. Everyone should have gotten this problem. So if you didn't get it, I'm not trying to scold you. I'm just trying to say, hey, you better look at what's going on, because if you can't do this problem, then the chances of you passing the final are not good. So that's just the reality after teaching this class for so many years. Okay. Any questions on this problem? Anything that was unclear or could have been clearer about it, or that threw you off? Okay. I tried not to make it anything tricky on this test, because I'm really not looking to trick you. I'm looking just to see what your fundamental knowledge is. All right, so let's look at the next one. We'll go through that. All right, oops, sorry. Okay, so here we have this problem. Now, again, I told you guys before when we did the test review, I said you will have a 3D equilibrium problem. So you knew this one was coming. Now, let's look at the elements that this problem has. You have this 70-pound mass hanging off of a plate. I told you that the tube is weightless. So really the only thing you have to worry about is the plate. You're given the 110 pounds is in the negative K direction. You have a tension AE, which is your cable going from E to A, and you have your bearing at B. Now I told you again, the bearing at B was a slider bearing, bearing at C was a thrust bearing. So you know that at C, you're going to have 3 reactions, including along the y-axis, but at B, you're only going to have an X and a Z reaction. Now, I told you in the problem, you only had to solve for B and AE, and that's because, for time reasons, because to solve for C just involved extra steps, which I didn't think were necessary. However, that doesn't mean that you can ignore C and pretend it doesn't exist. It's still part of the problem. So it's not correct to find. So for example, some of the moments about the y-axis to find AE, and that's fine. You take the Z component of AE and you sum the moments about C, then that'll work, because the 70 pounds has no input on that moment. But once you get AE, you can't use that to directly solve for B, because you don't know what C is, and that's the error. So you have to account for that. So what I'd hoped you'd do in this problem, what I wanted to see was you'd have your so here's your drawing of it, okay? And so you have your 3 reactions up here, your 2 reactions here, You have your tension EA. You have your 110 pounds going this way. And your governing equation, which I look for. So RB relative to C cross B, RG relative to C, which I called my weight. You can label it whatever you wanted. RD relative to C cross D, which is that. And E relative to C, which was this point here, crossed E, or what I should have written is probably I'll change that to tension EA, because that's probably a more accurate way to write it. But regardless, this is what you want to see. And this was like every other problem 3D equilibrium you show. It's the same thing. You draw the free body diagram, you pick the point with the most unknowns, take the moment about that, and then you just identify your R vectors. You have a vector going to B, from C to B. Remember, always going from here to here, from here to here, here to here, here to here. Or you could go to A if you want to live on the edge. So either way. So I went ahead and I wrote out the different RD relative to C, E relative to C, G, and B, and so forth. So these are your actual distances. You guys can go ahead and double check those. But I went through this problem several times to make sure. I had actually taken a problem out of a book and I changed numbers. So this isn't a problem you'd find anywhere. And then there's your tension, and that's the unit vector, which I gave you because I wanted to save you a little bit of time, figuring you all knew how to find unit vectors. All right. So once you've figured that out, then then you would take it to the next step. And this is really what I was looking for more than anything, was this matrix. I want to see this matrix. So here you have 0, and I know you know how to set this up, so I don't need to go through it. But if you don't know how to set this up, I would really, again, look at this, because this is going to come back to bite you in the butt on the final. I guarantee you there's going to be some type of problem like this on the final. So I would say that, depending on how you did on the midterm, there is still a chance to do well on the final, but you need to understand it. So the reason I'm saying this is because the overall, I'd say, performance on the test wasn't where I thought it should be. But, we'll see when I finish grading everything where the curve falls. So, again, you set it all up, set it equal to 0, and a lot of this drops out. So I just went straight to the I. So these are just my I components here. Negative 6.1 BZ plus 88 minus 2.473 TEA. 528 minus 2.76 TEA. So you can solve for TEA directly. A lot of you got the tension, no problem. And then you go ahead and you can plug that back into I and the K problem, and then you solve for your respective. So you get BZ equal to negative 63.1, BX is roughly 174. And that's the answers. So anything unusual about this problem? Any comments on it? Any questions? Makes sense now? Everyone knows exactly how to do it? So as you saw in my announcement, there will be a post-test evaluation, which is one of my colleagues is doing. It'll be a survey that I'll put on Canvas, and if you participate in it, I don't think I see what you say about it, because it's a survey, but I'll see if you participated or not. And if you do, then I will give you extra credit on the test. So I'm not sure how much that's going to be, but it will be something. So, I think the survey might take you 5 minutes, so it's probably worth doing. And when it's posted, I'll let you guys know. All right, so that's that one. That was worth 35 points. And then we get to the next one, the last one. This one. So does this look familiar to anybody? Have you seen this problem before in any way, shape, or form?
Yeah, I believe we did this one on an example.
That's right. It's exactly like a homework, or not a homework problem, but exactly like a problem I did in the example video. So, so I was hoping that, and some of you did this okay, and some of you, again, I given the audience, there's only about 20 of you, so and I haven't graded all of them. So perhaps all of you did this correctly. I don't know, but I don't know if it was a question of time or if it was just maybe you hadn't seen this problem or maybe hadn't looked at it. But anyway, this one wasn't supposed to be tricky, but it was. There's a couple of things about this problem, and if you hadn't watched that example, then it would be a little more difficult. But the idea with this is that it's a force couple system. So you're essentially moving everything to H, to that bearing down at the end. So you're not, this is a chapter 3 problem, so it's not equilibrium, you're not setting anything equal to 0. And so what you want to do is you want to identify all the forces acting and all the moments acting with respect to H. And so in order to do that, so first you have your diagram. So, and I drew this is, for some reason when I was drawing this, I drew 55 as going counterclockwise, but it's not, it's clockwise. So it actually goes clockwise. Whereas, so ignore that arrow for now, I gotta fix that. But the 18 and the 26, those, this is gonna be a more force is going counterclockwise than clockwise. Same with this, more force is going counterclockwise than clockwise. So these belts here are going to have a net counterclockwise or positive moment. This is going to have a net negative moment because it's actually going clockwise. So what you really want to do is you want to know the sum of the forces and the sum of the moments at H, because it's equivalent force couple system. So first thing is, what are the reactions? So the reactions are actually, the only thing the reactions in terms of forces are just these forces here. So we can see that in the negative Z direction, we have 32 and 8. So we have 40, right? And then in the positive Z direction, we have this little bit of we have this little tiny amount of, 5/13 times, so 5/13 of 26 is 10, right? 5 divided by 13 times 26 gives us 10 pounds. So you have this little bit of K, positive K. So you have 10 going up, 40 going down. So the net is negative 30, right? So I wrote it out here. I have negative 18. That's minus 12/13 26 in the I, plus 0J, plus 5/13 times 26 minus 40K. And so that works out to be negative 42I plus 0J minus 30K. That's your total force. That's all it's acting on it. And most of you got this. So and that was worth a small part of the problem because it's pretty easy. The rest of it now is you need to figure out what are the moments. So if you think about it, if this is my point H here, these forces here are going to be causing a moment about the x-axis, aren't they? Because they're trying to pull this and rotate it down around the x-axis. The same, and with this little bit of 5, that's also trying to rotate about the x-axis. And these forces in the negative x, they're trying to rotate about the z-axis. And then finally, the net belt tension is going to make a rotation about the y-axis. So you end up with forces times distances for all three. So if I think moment about h, it's going to be equal to r g relative to h crossed with negative 40k. So I go from here to here. When I get there, I have a negative 40 pounds in the k direction. And then I have plus rf relative to h, and that's going from here to here. And then when I get there, I have to cross that with the negative 42 plus 10. And then, and I may need to go back in and change a little bit of this. I think I erased some of it, but, and then Yeah, so you end up with, when you do negative 1.5 J cross negative 40 K, you get a positive 60 I. And you can do this doing the right-hand rule, or you can just whatever, J cross K, whatever's easiest for you to do. I use the little circle thing where I draw I, J, K, and then I draw a line in both directions to represent positive and negative, but whatever works for you. So if we do this over here, and sorry, it's a little, this is this side, and then this is this side. So this is RF relative to H is negative 4.5 J. And then if we do negative 4.5 J crossed with I, 42I and 10K, we get negative 189K minus 45I. All right. So, and then, so if we add that all together, we get 60I minus 45I minus 189K. And so, but when we subtract, we end up with a net 15I minus 199K. So this here represents just the moments created by these tension belts. All right. And the last thing we want to do is moments about the y-axis by the tensions. So now I know that in the problem it said 55 and I also put 52. So if you use 52 or 55, that was fine. Sorry about that little typo there. I thought I'd made everything perfect, but I made one small mistake. So you have a negative 55 foot-pounds. You have 32 minus 8 because you have a net positive rotation times the diameter of the times the radius of the pulley. And then the same thing here, 26 minus 18 times 1. And so the fact that the pulley has this 512 doesn't matter when it comes to the rotation about it, because it's still leaving the pulley at the radius. So where it goes from there is irrelevant, because again, we're only looking at its ability to rotate this. So once we do that, we end up with a net negative 29J or negative 26J if you use the 52 that I accidentally put in there. Either one would be fine. So you end up with a net answer of, with sig figs, negative 42, 0, negative 30, and then the moment was 15, negative 29, negative 189. So I know I went through that a little quick, but does everyone understand that? Does that make sense? Now that you look at it, can all speak at once? All right. Okay, so that's the exam. Again, I'll try to finish it up by Wednesday, get the scores back to you. I will post the scores, as I mentioned in the announcement, on Canvas. What I would suggest is if you want to go over your test in a shape or form, come to office hours and I can go over it with you one-on-one, and we'll, as needed. So one thing I did want to bring up is so week 6, the topic is not super challenging, I found, compared to other stuff. So, and since you just probably are starting it, there's not a lot to talk about just yet. So the centroids that we do in here are fairly simple. I don't do the centroids with integration because I know you guys have already done that in calculus quite a bit, and I don't think, and given how much material we have to cover in such a little time, it's not really beneficial to do it. So I just touch on centroids using composite method, basically taking known geometric shapes, adding them together. So we'll do 2D, 3D, one lecture 2D, one lecture 3D, and then we do 2 lectures on moment of inertia. One just basic moment of inertia, and then one using the parallaxis theorem. So the moment of inertia stuff is beneficial. That will something you will start if you take C204 next fall or in the summer or whenever you take it, if you have to take it. That's one of the key things you'll need to know right away. Mass moment of inertia, which is close kissing cousins to moment of inertia, that would be in dynamics right away. So both of those ideas are important. So resistance to rotation, that's really what moment of inertia is. farther you put your mass away from a rotational axis, the more resistance to rotation it has. And so I cover that in pretty good detail in my lectures. So, and the homework assignment's fairly short for both of those just because they're not there. Typically on the final, we combine this. So if there is a question on this topic, we combine centroids and moment of inertia in one question. So, but that's that. And so once you take a look at it, if you have questions, please come to office hours and I will do a short review on it next Monday. So for the quiz will just be a simple centroid question. So I would encourage you to look over the centroids. It will be it will only cover what was on today's lecture and nothing beyond that. So you should have, I believe Friday and Monday talks about 2D and 3D centroids. So that's what the question will be on. Any questions about anything? All right then. Well, thank you for coming. It's been a little short, but I will be in office hour from 10 to 12 if you have questions. Otherwise, you guys have a good day.
Thank you.
You're welcome.
Thank you.
Thank
You're
you.
welcome. You're welcome.